In the next section, I want to make the second statement about Huffman's algorithm. It gives an optimal prefix-free code, but we can also say how long that code is in more absolute terms. And that will involve the information theoretic entropy. The term has a history and it comes from physics, but nothing of that is really needed. We just borrow this word. The entropy is a simple quantity for us. If you have probabilities, some numbers that are between 0 and 1 and sum to 1, the probabilities for some outcome of a random variable, say a die with n sides, you can define the entropy as this sum. I think the last one is the one I find more intuitive. It's the sum of all possible outcomes, and then you take the probability for that outcome times log of 1 over the probability. Let me motivate a little bit why that might make sense. Or maybe we can do one tiny example first. If we take a standard die with 6 sides, and suppose that it's fair, so we would have all the pi are p1 up to p6. They're all 1 over 6. Then the entropy of this distribution is this sum, but the sum is always summing over the same term. So we can replace that by 6 times, and then pi is 1 over 6, and log of 1 over 1/6 is log of 6. And so that cancels out as log base 2 of 6, which is something between 2 and 3. Now, that's just some definition and some numbers. The intuition behind this formula is given by this yes-no question game, or 20 questions game. Your goal is to guess what is the random outcome of a random variable. It can take values between 1 and n. And you have to find out, someone rolls the die, and you have to find out by asking yes-no questions to that other person what was the number you got. And because you're smart, you do this in the best possible way, which is you always ask a question so that 0 and 1, yes or no, outcomes are equally likely. So for example, the outcome that we have is has a probability that lies here. So you lay out all the pi's from 0 to 1. You have an interval that's as long as p1 is. And then comes p2. I don't know, maybe a bit longer. That's p2. And maybe 2 more, p3 and p4. It always has to work out like this. It's a probability distribution, so it has to sum to 1. And now you may know this. You can generate a random output from this distribution by taking a uniform random variable in this range and output in what interval it fell. So maybe the random number fell here. And then you would say, oh, that falls into the interval for 4, so I output 4. Let's imagine that this is what happened here as well. And here's one outcome. That's the interval pi. And your question is, how do you find out that this was the random outcome? You don't know it, you ask your friend. So the first question you ask starts with the entire interval and asks, is it in the left or right half? That's the best you can do because it's equally likely to be in the left and the right half. So with one question, you can narrow down the range from the full unit interval to half of that. And your friend will tell you which one it is. And then you just keep going. You cut this in half again, cut this in half again, cut this in half again, until your friend has to say, or I mean, you know the picture I drew up here. the distribution is known to you. So if you want to find this point, it's enough to say, oh, okay, it's contained in this range. Then you know the output was 4, because there's all entirely contained within this P4 interval. So at this point, you can stop here, and you only needed 4 questions. And if you count how many times you have to cut in half before you lie inside this interval, you get to essentially this log of 1 over pi. There's a bit of rounding involved. If it doesn't work out nicely, like in this case, that you get exactly the boundaries, then you may need 1 or 2 additional questions. You can always get away with 1 more at most. But the entropy says, let's ignore the rounding. Suppose you can always make your questions work out to have the exact right place. Then you would need log of 1 over pi questions. And so the total sum is the expected number of questions you have to ask. That's an intuition for the entropy. Now, how does that connect to compression and Huffman codes? The decoder basically asks the same question. The decoder wants to know what's the next letter, and it asks you questions of yes and no type. Am I in the left or in the right half of the Huffman tree? That's sitting at the root, and you have 0 and 1. And it keeps asking questions until it has narrowed down 1 leaf. That's your letter. So it's not so far away from that, really. All right. So what does that have to do with Huffman codes? If things work out nicely, we would like to encode something with that probability pi with log of 1 over pi bits. But that number may not be an integer, so we can't really do that. But we can prove the following. If we have an alphabet with weights, as before, the input for Huffman, Huffman computes some code words E. They all have integer lengths because they're actual bit strings. Then this L of E, the expected code word length, the average weighted over the weights for the characters, it lies always between the entropy and the entropy plus 1. And so it's very narrowly sandwiched between these 2 bounds. And the entropy is if you define characters to have probabilities. So you take the weights and normalize them by the sum. I don't want to prove this formally, but I want to give you the key ingredients. And this is something often done in undergraduate classes. The first bound is you can't beat the entropy. So what Huffman spits out is at least as good as the is at least as costly as the entropy says. And the key for that is to use Kraft's inequality, which means whenever you have a code trie, then if you sum up these numbers, the length of the code word as a negative exponent of 2, which is the depth in the tree, if you want. That's the length of the code word. Then that sum is equal to 1 in a proper code trie. So for example, in this one, you would start with 1 at the top level. Then you cut it in half if you go 1 level down. You split the 1 once. If you go to the next level, you split it in 4s. And one of the 4s is staying here. So you have 1/4 weight that's used on this rightmost leaf. And you go 1 level further down. Now you're at 8s. You cut it in half again. And so we have 1/8 4 times here. And if you sum that up, you should get to 1 if you add the other leaf that I forgot. There's another 1/4. If you always make the tree full, so there's no gaps, like this one had a gap, that's not good. If you add that in, 2 times a 4th and 4/8, that's 1. That's Kraft's inequality. And the second Gibbs inequality is an analytic property of the entropy. If you take this formula for the entropy and replace this pi with any other numbers that sum to at most 1, then you make the sum bigger. For that, you'll just have to believe me for now. It's simple to prove with just the slope of the logarithm. Logarithm is a concave function. If you insert what we know now, this is the entropy, and this turns out to be exactly the code lengths of the QI are the code lengths in the Huffman code. So if you insert this here, you see it's just canceling the log and the 2 to the minus cancel. And then you get back to the sum for the Huffman code. So that's that part. Huffman codes are never better than the entropy. And the other part is they're never worse than the entropy plus 1. For that, you do something that Huffman could do. So you take log of 1 over pi, which is the ideal length, but it could be any real number, so you round it up. And you can show that there's a code that has these lengths as the code word lengths. If you do that, you end up with at most the entropy plus 1, because rounding up gives you at most plus 1. And you can construct the code for this basically using this procedure. I think I'll skip the details here because we're a bit short on time, and we don't build on this later. So if you're curious why that's true, you can read the details up. We won't really need it. What I wanted to take from this, though, is the meaning of this theorem. And so maybe let me go back to the theorem. We were 38 earlier for the attendance code. I don't know if you still voted. Let's wait for 35 at least. Five more. Four more. Two more. Yeah, there we go. Okay, works. So I think in a way the third answer is not quite correct, but this is a trick question in the sense that it depends how you exactly interpret the question. Let me go back to where I can write. The first one is not wrong in the sense that we've just had this proof that Huffman computes a best possible prefix-free code, it turns out that any fixed-length code is also prefix-free, obviously, because if they're all the same length, nothing can be a proper prefix of anything else. So Huffman codes are always better than a prefix-free code in terms of the expected code word length. So if you mean by more efficient compression the expected code word length, then Huffman codes are never worse than any fixed length code. In the same interpretation, if the entropy of the character distribution is less than log sigma minus 1, then even after adding the +1, which was the best bound we could prove, we're still strictly better. If you're in this range, where the entropy is just strictly less than log sigma, you may be better or you may not. Depending on where on the scale, the expected code word length could be between h and h+1. If you're closer to the h+1 part, but h is just slightly less than log sigma, you're not doing really much better. Now, in a way, if you look at this more closely, the fixed length code would also not achieve log sigma, but log sigma rounded up. And whenever log sigma rounded up is close to log sigma, also Huffman would be close to that. All right. In a way, there's not too many wrong answers. But that's maybe something I didn't point out. The entropy is at most log sigma. That's just because it's not completely obvious. This sum that the entropy has is a sum with the concave function, and so it's maximized when all the arguments are the same. So the entropy is maximal if the distribution is uniform. And then we've seen the example with the fair die, where you had 6 outcomes and the entropy was log of 6. And the entropy is never bigger than that. But it could be close to 0. If the entropy is very close to log sigma, then Huffman codes won't help you that much. If the entropy is much, much smaller, say, for example, like this, then you definitely save with a Huffman code. All right. Putting that all together. So what we've seen before already in the discussion of the code, sigma log sigma is the implementation with the priority queue, where we use a heap, binary heap. And more precisely, we have to build that initially from all the alphabet symbols. And then for all iterations, we use 2 delete mins and 1 insert. Now there's a useful special case if the alphabet is already sorted by weight for some reason, or because you've made it so. Once you have that, you can actually do it faster. You can do it in linear time using just 2 queues. It's a cute little algorithm to figure out. Just leave it with that comment. Once you have the Huffman code or the code trie constructed, the time for encoding the text is essentially just as long as you need to read the text. You have to read every symbol, and then you have to write the output. But you can prepare this code word table so that each character is a constant time lookup. The key algorithm is like I presented, but there's many variations you can use. The type breaking rules is one, where you can go in different directions. The way how you get the weights can be different. You can, as we did, you just count exactly how often each character occurs. There's cheaper ways where you just try to guess that, and there's ways where you're adapting. So you say you just keep counting, but you already encode the character at that point. So at each step, you use different weights. You use the weights up to that point. And you can, with a different algorithm, much more complicated than the simple one we've seen, you can keep the Huffman tree up to date while you work your way through the text. What's good about Huffman coding? We had an optimality statement. It's always great. It's the best possible, but it's the best possible in some specific sense. I stressed this many times in this module. Whenever someone says optimal, be a bit careful what exactly that means. So here it's the best possible prefix-free character code, but it's very fast, and so that can be very convenient. One downside is that it needs these 2 passes over the text in the version that we've discussed. And another downside that also refers to this last Slido question, if you factor into this that for a Huffman code, you have to also tell the other side what code you used. It's not so clear if it's a big win, only for long enough texts. Or for the fixed length character code, you also have to tell the other side which ones you're using. But it's a downside of Huffman codes. You have to tell the decoder what the code looks like.